Now that we understand the basic concept of a limit graphically, we're going to go over some of their properties before we jump into limits algebraically. First, let's get technical with our math lingo. Let b and c be real numbers, and let f and g be functions with the following limits. The limit as x approaches c of f of x is going to equal L, be represented by L, and the limit as x approaches c of g of x is going to be represented with a capital K for the following definitions. So the first property we're going to look at is the scalar multiplication property. This property states that if we're multiplying a function by some sort of scalar, and we're trying to take the limit of this function, then we can actually just pull this guy right out front and continue with our algebraic limit of the function itself. Then once we actually evaluate the limit as x approaches c of f of x, we'll take the scalar and multiply it by that new value. The next property we'll talk about is the sum or difference property, and this one's pretty intuitive. If you're trying to find the limit of a sum or difference of two or more functions, we actually get to break them apart and take the limit of the individual pieces, which would look something like this. And then at that point we can actually evaluate each of those limits individually and add or subtract those two y values that they each approach. Now, something to keep in mind when doing a lot of these properties is that if there's even just one of the limits that does not exist, then obviously combining it with another function, another limit of a function, is also going to result in something that doesn't exist. So just keep that in mind. The third property will be the product property. And this one's really similar to the sum or difference, where we can just break them apart, evaluate each limit separately, and then find the product of those two limits. This leads us to the fourth property, which is the quotient property. Again, same concept of simply separating them into two smaller pieces that we can evaluate separately. Now this one is definitely more prone to cause problems if we're not paying attention, because not only do we have to worry about an individual limit possibly not existing, but we also have to worry about this denominator not approaching 0, right? So if the limit of as x approaches c of that bottom function approaches 0, we know if we divide by 0, it causes us to get something undefined, in which case the limit would not exist of this entire expression. So we've got two more properties left, and these are the ones that are a little bit trickier. So the next one covers two scenarios, really, because it's dealing with exponents. And if you remember, roots have to do with rational exponents, like if it's to the 1/2, that's really the same as the square root. So just make sure to keep that in mind as well. So if you're trying to find the limit of a function that has some sort of exponent or is inside a radical, you basically can kind of keep it to the side and evaluate what's in the actual function, and then just raise the actual limit y value to that power. So to me it makes more sense to kind of see it in this form, and then you simply evaluate that limit and then raise that result to that power. And again, this is assuming that r and s are both integers, and just like the last example, we don't want 0 in the denominator, so as long as all of those criteria are met, you're good to go. Our final property deals with the composition of functions when you're finding limits, and this one was the one that was the least intuitive to me the first time I was doing these. However, after I did more of these problems, it started to look more like, kind of like the one we just did, where when you do a problem like this, you basically focus on what's inside and leave the thing that's outside for after the limit's been evaluated. So in this case, it would look like this, and we would go ahead and evaluate that limit for g of x, and then find f of that y value it approached. And that's all you have to do for that. So let's do a couple quick examples just so you can get a better idea of what this will actually look like. And before we jump into doing algebraic limits, we're going to start with these that are kind of already defined for you, so you don't have to actually plug anything in or simplify anything. I'm just going to tell you what the limits are for the two functions, and then you're going to use that with the properties. So let's do our first example. So the limit as x approaches c of 5 times g of x. So something to be warned, one of the most common mistakes here is just like looking at the wrong function. So don't let that be what trips you up on these. So this one's talking about g of x. Our property said that with scalars we can basically just pull them out front and then evaluate the actual function as normal. So in this particular example, we're going to just pull that 5 out front, and it was defined for us at the top that the limit as x approaches c of g of x is equal to 3. So I simply can just plug that in. And so we get an answer of 15. Alright, let's try a second example. The limit as x approaches c of the sum of f of x and g of x. So let's look back at this one. And this is the one that simply says we get to break them apart into two separate limit problems. So the limit as x approaches c of f of x is going to give me 2, plus the limit as x approaches c of g of x, which gives me 3, and in this case we are adding them. So for this one we get an answer of 5. Alright, third example. This one is dealing with the product property, which is very similar to the sum and difference. We basically just keep them as separate pieces. So this one would simply be 2 times 3, which would give us an answer of 6. Alright, our fourth example deals with the quotient property. And so we simply, again, evaluate each separately. So the limit as x approaches c of f of x we have established is 2, and for g of x is 3, and so we simply get this fraction 2 over 3. Again, pay extra close attention to what's happening in that denominator. We do not want a 0 there. If there is a 0, it would be a limit that does not exist. Alright, another quick example here. This one's dealing with that power or root property we talked about. So again, you're basically going to kind of evaluate it inside and then square that result. So that makes it easier for me to see what's going on. I know that the limit as x approaches c of f of x is simply 2, and so that just gives me 2 squared, which will give me a final answer of 4. And for the composition example, we can only go so far with the information I've given you, but we can at least start it so you can get a little bit of the hang of it. So the limit as x approaches c of f of g of x, let's just go with the standard here. And remember, similar to that power one, we would just kind of pull that outside piece open and take the limit of what's inside. And we know the limit as x approaches c of g of x is a 3. And so this type of problem, you would have to have more information to actually get a final answer. For us, this is as far as we can really go, because we don't know enough about the function to actually evaluate it at 3. This concludes your properties of limits video. We're going to be jumping into algebraic limits next, where you will definitely utilize this information.